Okay, everybody, today we're going to be looking at some advanced heat problems. Okay, so this is a little different from what we've been doing before because in this part, we're looking at how things can be placed in contact and heat flowing between objects. So when we do this, just a little introduction to it, is the science of using heat and measuring heat is going to be called calorimetry. I think we talked about that a little before in the past. And this can be used to do a variety of things. Number one, we can use this to identify something, an unknown object, through heat transfer. We can also, if we're given two objects in contact, we can find a final temperature that will result as one transfers heat to the other. And we can also look at the energy content in food. So this is used that way. We may not be doing a food calorimetry problem here, but it can be used for that effect. So one thing we want to be sure of is that we can use other objects. Again, we don't always have to use water. We can use heat calculations to apply to other objects, such as maybe copper or aluminum or gold. And if you want to do that, you have to make sure you use a specific heat, okay, of a different object. So if we go to my pen here, just hit the right color here. All right, what we can do is we can use the specific heat to answer this question. So the specific heat of copper is a lot lower than water. You can see at 0.39, it's definitely lower. Okay, so that would make it easier. Okay, easier to heat up because the heat capacity is very low. Okay, so water being 4.18 means you need that many more joules to increase the temperature of water. So with copper, you need a lot less. So metals usually are going to have a lower specific heat in this way. All right. So let's just say we wanted to use this to answer a problem. It's kind of easy to do. So how much energy would it take to heat up a certain mass of copper from 20 to 100? Again, we can use quickly our Q equals MC delta T on this, right? Quick little formula. Okay. And again, if we wanted to use, Q is our X, M being our mass of 5.20 grams. Okay, C in this case would be 0.39 joules per gram degrees Celsius. Okay, and our temperature change here, the change in T, is going to be 80 Celsius if we look at the 20 to 100. So again, if we wanted to put this together in a formula, we could say Q equals the mass 5.2 grams. We could times that by 0.39, and we can times that by 80 Celsius. Okay, and then we'd end up with 162.2 joules. Okay, just make sure you have the right unit. That would be important. All right, so that's pretty easy problem. Just want to go over something that would be involved with something besides using water. Okay. The next part is a little interesting to show you how heat capacity works when you're using different objects. And let's just say you apply, someone applies 300 joules to 5 grams of copper. So we're going to do 300 joules to 5 grams of copper. Okay, initially at 10, and then you're going to do another experiment, but use 5 grams of water instead. How do we calculate that final temperature as a result? So if we take, for the copper end of it, I'll do the copper experiment here. Say we had delta T, okay, is going to equal Q if I rearrange the formula over MC. So that would be what we would be using, right? So if we use the stuff here, we would say, okay, 300 joules, okay, you're going to divide that by the 5 grams of copper, okay, and you're going to times that by the 0.39. Okay, and what we're going to find is that the delta T in this case, okay, is going to equal 154 degrees Celsius, right? And that's the delta T. So that's how much the copper would go up. However, if you add that to the 10 Celsius initially, to where it's starting at, you would end up getting 164 Celsius. All right. So that would be my final temperature if you added 300 joules to the 5 grams of copper. All right. If you did this for water, okay, it's an interesting effect that you see where we're going to do the same thing. We'll say delta T is Q over MC, okay? And then really quickly we'll have 300 over 5 grams of water. But instead, we're going to multiply this by 4.18, our delta T being 14.3 Celsius plus 10, okay? Which would end up being my 15.3 Celsius. So what's interesting about this one here is that here's your final temperature using water would be 15.3 if you're initially at 10. But if you used copper, it would be 164. So what does that tell you? What that's telling us is that, again, the specific heat being so low that a lot of the heat, okay, is being transferred to raising the temperature, where in this case, the heat is being used and absorbed rather than raising the temperature. So that's another way you can look at this. All right, if you move on and get increasingly a little bit more here, talk about something a little different in this case, is something when you have two objects in contact. So in this case, what I'll do is go to my pointer again, pen, okay, pointer, pen, color. Okay, and we go back to our pen in this case. Sorry, guys. Let's go to my pen. Little pen difficulty here. There we go. All right, so we're going to look at number 3, and we'll do this like we'll take care of this in steps. All right, so suppose we're mixing 90 grams of water, hot water, with 10 grams of cold water. So that's a little different, right? So let's just say we're taking 90 grams of hot water, okay, at 90 Celsius, and we're going to mix with 10 grams, so a lot less of this, 10 grams of cold water, okay? And we want to know where this is going to end up, okay? So really there's 3 problems here. So we're going to set up an expression for the energy released by the hot water. All right, so let's see what we're going to do. We're going to take, we'll do Q of the hot, and here's your expression. So we can say Q is going to equal to, of the hot, is going to equal 90 grams of water, right, times 4.18 because you're dealing with water, okay? And what we're going to do here is something kind of interesting because, again, we know that the hot water is going to cool down and we know the cold water is going to cool up. So the final temperature here we know has to be between the two, right? So if you think about it off to the side here, we know that 90 Celsius is the hot and 10 degrees is the cold. So we know the final temperature is going to have to be somewhere in between. That's the key, right? So we're going to definitely cool down to X, but heat up from 10 to X. So what I want to do is try to keep this term positive. So what I'm going to do is I'm going to take 90 here. I'm going to minus X in this case. So because we know that this is going to be a lower number than 90, that keeps this term positive. Okay? And this being the new temp. All right? Now, if we go to B, now there's nothing we can do here, right? We can't do anything with this equation because I don't know X, and then, of course, I don't know Q. So you're kind of in trouble here. All right, so you have an equation with 2 unknowns, which we can't solve. So let's look at the expression for the cold water. So I'm going to say 90, we'll take, 10 grams of cold water, again, times the 4.18, all right? But in this case, if I look at my temperature thing, I'm going to see that the 10 is going to heat up to some higher temperature, X. So I want to keep the term positive, so I'm going to put X minus 10, okay? Where again, this is the same X as up here, so it's the same new temperature. So that keeps this term positive here and this term positive here. Again, we can't answer this, right, directly because we have 2 unknowns. So what we do know is that the hot, okay, heat released is also heat absorbed. Really important. We know that the heat released by the hot water is going to be the heat absorbed by the cold water. So we can say the hot is equal to the cold. So we're going to take Q of the hot and equal Q of the cold. All right. So we're going to set those expressions equal. So we're going to take the Q of this equation versus that equation. So I'm going to say 90 grams times the 4.18, okay, times 90 minus X, okay, is equal to the Q of the cold, 10 degrees times 4.18, okay, times 10, is X minus 10, okay? So you just, basically, Q of the hot equals Q of the cold, so MC delta T of the hot is actually equal to MC delta T of the cold, right? Because we talked about conservation of energy. Heat lost by the water must be gained by the cold water. Again, we're assuming that this is completely insulated, right? This is a completely insulated system here. All right? And the rest is just algebra. So I can show you this here. One thing we can do, if you notice that on both sides of the equation is this 4.18, so we can get rid of that. So basically what we'll have is if you distribute the 90 to the 90 minus X, again, I'll do the quick work for you. You'll have 8100 minus 90X equals 10X minus 100, okay? And eventually, if you collect your terms and do what you got to do, you will have 8200, okay, minus 90X, okay? And that's going to equal 10X on that side. You do what you got to do. We got 8200 equals 100X, okay? And then X is going to equal 82 Celsius, okay? Which makes sense because if you take a look up here, because you have a lot less cold water and you have a lot higher amount of hot water, you wouldn't expect the 90 to cool down all that much. So you would expect this to be maybe closer to 90, and exactly that is what we find. So you can predict this to be, all right? So again, a different type of problem. And the key to the problem is the fact that you're mixing two things, right? In this case, two things are in contact, all right? And you're mixing, two things together, all right? What I want to do is give you one more type of thing that we can do with this, and I want to do a problem with you that would be a little bit different. Okay, so we'll move on to this kind of question. Okay, and this is the last one that we'll do here, I think, because I think this is easy enough to do. We just have to figure it out. So we got 175 grams. I just want to make sure my pen is good here. All right. So we have 175 grams of hot aluminum. Okay, and we're dropping that into an insulated cup that contains 40 milliliters of ice cold water at 0, and we want to figure out what the final temperature will be at. Okay, and again, don't get crazy with all of this. Remember, you're dropping this into something else. So let's just do a quick little diagram. We have an insulated cup. Okay, we got 40 milliliters of water in here. All right, we got some water in here. Okay, it's at 0 Celsius, 0.0 Celsius. Okay, so we're starting at that point. Okay, we know C is 4.18 of the water. That's easy. We know the specific heat of the water. Okay, and then we're taking 175 grams of hot aluminum and we're putting that in the water. Okay, and again, that has the initial temperature of at 100 Celsius. Okay, so we're taking hot aluminum, putting it into cold water. All right, so we know the hot aluminum is going to give its heat to the cold. All right, so we know that's going to be fine. All right, so we're going to find expression for the heat lost by aluminum. So Q of the aluminum is going to equal the mass of the aluminum, right, times the specific heat of aluminum, which they give you, 0.900. Okay, and again, we're going from hot aluminum. Okay, we're going from hot aluminum of 100 to cold water at 0. So where is this going to be? We're going to end up somewhere in between. Now, just a little trick here. When you want to find that temperature unit here, or that temperature factor here, you can take this and look at that as your temperature factor, 100 minus X. Isn't that a little trick? So you're going to take 100 minus x just by looking at this little diagram, and the cold one will be x minus 0. So it's a good way to see this. So this is going to be 100, minus x. That's what that is. Okay, so we have our expression for hot, and now we're going to look at our expression for the cold, which is going to equal to 40 grams of water, right, times 4.18 times x minus 0. Okay, again, you want that term to be the positive term. All right, so we're in good shape here. Okay, so now because the aluminum is going to give its heat to the water, we're going to set those two equations equal. That's the key here. Okay, and then we can solve because heat lost equals heat gained. Okay, now again, we're assuming this is insulated. So we'll take this equation here, and we'll equal that equation. So we'll take 175 grams, okay, times 0.900. We're going to times that by 100 minus x. I'm going to set that equal to 40 grams times 4.18 or 4.184. Sometimes you see that. Okay, and this is going to be x minus 0 Celsius. Okay, and then we can solve. All right, so I'll do a little of the algebra here. You're going to have to finish the rest of it. You're going to take 175 times 0.9 times 100, okay, and you get 157.50, okay, and then you're going to take that 175 times 0.9. You're going to distribute it to the x, so that's going to be minus 157.5 x, and that's going to equal the same. You're going to do the same thing here, okay, and that's going to equal, again, this 0 cancels out, so you're going to get 167.36x. Follow along, and then you can take 157.50, okay, equals 324.86x when you collect your terms, okay, and x is a grand total of 48.5 degrees Celsius. All right? Now, check that up where you should be. Are you between 100 and 0? Yes, you are, okay? But listen to this, right? You have a lot more, you have high heat, but also you have a lot more mass of aluminum too, right? But you only have 40 grams of water. It's starting at 0. So you'd expect it to heat up to a certain amount. Expect that aluminum to cool down very quickly, okay, because its specific heat is very low. All right, so again, the next two problems, question number 5 and question number 6 on page 13, and question number 14 on question number 7 and 8 on the next 2 pages. So page 13 and 14, numbers 5, 6, and 7 and 8 are all very similar to these problems. So you should do numbers 5, 6, 7, and 8 on pages, on this page 13 and 14. You will be quizzed, or I should say quizzed, you'll be tested when we have the energy test on these. I would do them, check the answer keys, come back in class, talk to me about it, and we should be in good shape. I hope this helps. Have a great day.